Everyone, let's get started. So welcome to the second session on types. We're going to have 4 talks in this session, and the first talk is going to be given by Andrea Laretto, and it's a very nice title. Di is for directed, first-order directed type theory via dinaturality. Thanks.
Okay, thank you. So welcome everyone. Thank you for being here. My name is Andrea, and these are my PhD supervisor, Fosco and Niccolò. And okay. These are my supervisors, Fosco and Niccolò. And today I'm going to tell you about a simple way to do directed type theory. And to do that, we're going to use a notion from the 70s, actually, that we're kind of resurrecting it to do directed type theory precisely in a simple way. And that turns out to be the right notion. And the pun in the title is because the di in dinaturality stands for diagonal. But we're using it for directed type theory. So what's the big idea? Category theory is hard. I hope you can relate to that. It's especially hard to understand. But we all love logic, right? And type theory. And so the claim of this talk is that category theory has a lot in common with logic, actually. And I don't just mean that you can use category theory to do models of logic and type theory. I mean it in the sense that the definitions of category theory and the theorems of category theory are very much related to logic. So, for example, let's start with a simple equivalence, logical equivalence in first-order logic. So P of A is in logical equivalent to say just for some constant A. For every x, if x is equal to A, then P of x, right? And what does this look like in directed type theory? Well, it looks something like this. So we just replaced the if and only if with an isomorphism. The for all with this very interesting integral-looking symbol called an end. And equality, this is going to be very important, is replaced with hom. And hom represents the hom set, the morphisms of a category. And if you understood this correspondence, congrats, you just understood the Yoneda lemma, the infamous one. And this is the actual one that category theorists use, so it's not just some representation in Haskell, for example. And the idea is that we want to be able to prove the Yoneda lemma in the same way that we can prove the logical equivalence above in type theory or sequent calculus. And so how would we prove something like this, the equivalence in first-order logic? Well, we start with a definition here in some generic context. And this is first-order logic, so we have a context of variables. And then if you read it from top to bottom, we can do for all introduction, so we can just remove it and put x in our context. Then we have an implication here, so we query it. Now we have an equality, and now we can do substitution, and we're done, right? Well, this is what it looks like in our system, the corresponding proof in directed type theory. You can see it literally has this same exact structure, right? So just to give the setup, let me recall the rules of equality. So in the type theories that you know already. So you have a rule for introduction, which just states reflexivity of equality, of symmetric equality. And then you have a rule to eliminate them called the J rule, or equality elimination rule. And just says that if you have an equality in context A equals to B, and you have some A and B's appearing in your formulas, then it's enough to prove this P, for example, in the case where A and B are the same and identified with the same variable Z. And from this automatically follows that equality is transitive. You take the statement, then you take B and A here, you substitute them with the same variable, and then you're done. This is an axiom. But you can also prove that equality is symmetric, automatically using the same principle. You just have A and B, B equals A, and then you substitute them with the same variable, and then you're done. That's just refl, right? So one of the big ideas behind homotopy type theory is that actually the proofs of an equality, you can have more than one, right? And so the idea is that you interpret types not as just sets of elements where these are the inhabitants, you interpret them as groupoids, so where the morphisms are exactly the equalities of which there can be more than one. So what is a groupoid? A groupoid is just a category where all morphisms are invertible. And they're invertible because equality is symmetric. That's why it works. And the idea is that whenever you're proving something about equality, you're actually secretly proving something about groupoids and groupoid theory. And if you take that a step further, you can prove something about spaces and homotopy theory in HOT. But the natural question is, what about categories? Why do we need this assumption here, right? And groupoids are categories. So we kind of want to scrap that, and now we want to do the same thing, where types are categories, and equalities, quote, are, you can have more than one, and they are directed, right? They have some directionality. And the idea now should be that whenever you're proving something about this kind of direct asymmetric equality, you're actually secretly proving something about categories and category theory. And now, if your types are categories, you can use your type theory, your proof assistant, as a unifying framework to talk anything that is asymmetric directed, such as rewriting, processes, transitions. Anything that you can use category theory with, you can do in your type theory, ideally. And so the type theories that you know and love are all about symmetric equality. Directed type theory should be the syntax that supports this kind of interpretation with directed equality. And so your types become categories, and intuitively, what should happen next, that your terms become functors, or something like this, right? And that your equalities are exactly the morphisms of your category. And now, because you have categories, types should have a notion of polarity. If C is a type, then C-op should be a type too. And C-op is just the opposite category, where we just take this type and reverse the direction of the arrows. And now that we have this structure, we can say that equality types instead become hom types. And because equalities are asymmetric, we kind of have to put this op on the left side because morphisms are contravariant on the left. So how does this analogy continue? This connects category theory and logic. Well, reflexivity of equality should just be the fact that categories have identities. And transitivity of equality is the fact that in categories, well, you know, you have composition, right? The fact that for any function f, which now is a functor, the equality is always respected, is represented by the fact that functors have an action on morphisms. So you see the connection here. And then the idea is that you have for predicates, you can think of them as presheaves in the semantics, and transport becomes just the fact that these have a functorial action. And now, interestingly, point-wise equality of functions become the notion of natural transformation. Again, here we're using this integral symbol called an end to represent the for all here. And again, equality becomes this hom type. Now, directed type theory has proven to be very elusive, and there are some problems that you kind of need to solve in order to deal with it. So the first one is that you kind of want to state, for example, that equality is reflexive, right? And then, how do? You just say hom xx, right? But you're using the same variable x both on the left side and on the right side of hom. But in the semantics, we know that hom has this kind of asymmetric vibe, right? So the question is, what is the type of x? Is it C-op? Is it C? Is it both? What's going on? And one of the solutions that has been explored is the fact that you kind of want to go back to groupoids. But that feels strange, right? I thought the whole point was to go into categories and away from groupoids. The other problem is that how do you avoid symmetry in the rule for J, for equality elimination? What kind of syntactic restriction should you put? Because I kind of want to be able to derive transitivity, for example, for free. So I want to do something like this, right? But at the same time, I don't want to derive symmetry, right? So how do I change J? And actually, you can see that the same problem with polarity appears here. You have this B that appears both on the right and on the left of a hom, right? So that's a bit weird. In this work, we present a first order, so it's non-dependent, directed type theory, and it's a type theory because it's proof relevant. And we solve these two problems exactly using dinaturality. And dinaturality solves the polarity problem without having to use groupoids. And it tells us precisely what kind of syntactic restriction we should put on the J rule to avoid symmetry, but recover all the other interesting theorems. And also tells us what the directed quantifiers of directed type theory should be. They are ends and coends. And from this, we get a very simple algebraic description of directed type theory that follows the same steps of Martin-Löf type theory in that sense. And we get out of this logical proofs of theorems in category theory that we can reinterpret logically. And so the setup is basically this one. You can think of in your head of this system as first order logic, but your sorts are interpreted in the semantics as categories, functions are as functors. And then you have the logical part. You have predicates or formulas. And these in the semantics will be dipresheaves, so functors of this shape, among which you have equality predicates, so hom. And then you have entailments between these formulas, which are in the semantics dinatural transformations. And the quantifiers for all and exist are represented by ends and coends with this. Again, integral symbol, and coends exists and just has the same index but at the top. That's just the notation the category theorists use. So this is how it works. We have a judgment for types, and it's pretty simple. You have whenever C is a type, C-op is a type. Then you have the product and function types, top. And in the semantics, these are categories. So for example, this is the product of categories. And this is the functor category from C to D. Then you have a judgment for simply typed terms, which in the semantics are just functors. And they're also very boring. These are exactly the same rules that you've seen in simply typed lambda calculus. The only interesting one is this one on the right that says that whenever you have a functor from gamma to C, you also have this opposite from gamma op into C op. Then you have a judgment for formulas or predicates. And in the semantics, these are dipresheaves again. These are the constructors. You have top, you have conjunction, then you have implication, and this one is actually interesting because you have this small op on the left, on P, because intuitively implication is contravariant, right? Then you have the rules for quantifiers. And then the interesting part is the case for hom predicates. So this, in this formula, there are two terms, S and T, and there are two key ideas. The first one is that S is given type C op, as you might have expected from the previous slides, and T has type C. And the other key idea is that in the context of these two terms, I put both gamma op and the context concatenation gamma. And so I can have two copies of gamma that I can choose from in S and T. That's the key idea. And so these two copies are intuitively connected. So whenever you have some x in gamma, then you have, as notation, we say that x bar has type C op in gamma op, so the one on the left. What do we use this for? The idea is that we can use variables incorrectly, so regardless of the outermost op. And this is precisely used to solve the polarity problems I told you in the beginning. So if I want to state reflexivity of equality, I can just use, on the left side, I use x bar, and intuitively it's connected to x. If I want to state transitivity, now I can solve precisely this problem with the B, right? So A here has type C op, so I can just put it here and here. Then I have B of type C. And if I assume that it has type C, then it can be here, but it cannot be here, right? So we have to use it incorrectly there. And then in the statement of symmetric equality, right? You want to say that equalities are symmetric. If you have an equality from A to B, then here I have to use B and A. And these have to be used incorrectly if I assume these types here, right? Because if it appears here, it cannot appear here, and vice versa. And we say that the variable is used naturally, or it's natural, when it's always used correctly. So it never has the overbar. And we say intuitively that it's dinatural when sometimes it's used correctly, sometimes it's used incorrectly. Now, intuitively, you should think, well, now I have these x and x bar, but these are, in principle, different variables. I just put two copies of the context, right? So they should be joined somehow. And the idea is precisely to give them the same value later in the semantics. And this is exactly the idea behind dinatural transformations. Okay? Maybe you don't need to understand all the details, but that's the key idea. So now we have entailments in our logic, and they look a little bit like this, right? You have some phi, which is just a list of predicates, and then you have that x bar and x and y bar and y appear all over your entailments. And in the semantics, what this becomes is just a family of functions between sets. And the key idea now is that I say for every x in the objects of this category and every y, I just instantiate both the x bar and the x with the same concrete value from the objects of this category, right? And then this family of functions in a set has to satisfy one very cute hexagonal-looking equation that I'm not going to show. The problem is that this hexagon, this equation, is not compositional, so it's very weird. And so that means that dinaturals do not always compose. And in practice, in your type theory, this means that sometimes you cannot do substitution. That's very weird, right? The takeaway from having used this type theory and experimented with it is that in practice, dinaturals compose whenever you need them to. Okay? And the reason for this is that the most common reason why they compose is that dinaturals actually compose with natural transformations, the ones they already know, both on the left and the right. So the idea is that if you have some situation like this, P implies Q, Q implies R, then in our type theory, you capture this very simple case with this complicated looking rule, right? But the idea is just that P implies Q, Q implies R, P implies R. And the one in the middle here has to be a natural transformation, so you have to impose some restrictions on the way that variables appear. Now, finally, you can state the rules for directed equality. So we can say that directed equality is reflexive, again, using our idea that I showed you before to solve the polarity problems. And now, this is the key idea. This is J. This is what J looks like. And this is how you read it. If I have a directed equality E from A to B in my context, I can contract it only if A and B appear correctly in the conclusion here, and A and B appear incorrectly in the context. This is the syntactic restriction. If that happens, then it's enough to prove that P holds on the diagonal Z, and that's precisely why they're called diagonal transformations, dinaturals. So just from this rule, you can derive for free transitivity of directed equality. So this is the statement, right? And now we can choose to contract the first equality like you would do in a proof assistant. You just choose to do induction on the first equality. And the idea is that now we can apply J in this case specifically, because A and B appear correctly in the conclusion. B bar does not, it's just A here. And they appear incorrectly in the context. Here we have just this B bar, A does not appear, so it's fine. And because of this situation now, we just are reduced, we reduce to exactly what you would do in a proof assistant. So you just take A and B, identify them with the same variable Z, and now you have G, and you're done. That's an axiom. You also get that terms are functors. You get this for free. You have an equality here. Then you have hom FA, FB. You take A and B, identify them with the same variable Z, and then you're done. And then you also prove transport for free. So if you have P of A into P of B, you just here do contract A and B together, and you're done. And now, the syntactic restriction does not allow us to get that equality is symmetric. Why? Let's see why. So J says that A and B must appear correctly in the conclusion, but here they appear only incorrectly, so exactly the opposite of what you want, right? And the interval is a counterexample. So here I'm just illustrating why the syntactic restriction does not work, but in general, this is not derivable. Then actually, our entailments have a computational content. They are functions between sets. So we have a judgment that says when these are equal to each other, pointwise. And this allows us to state the computation rule for J. So if you have J, and then you substitute the equality with Reffel, you just get exactly the hypothesis you started with. This is exactly the same as in Martin-Löf type theory. And from this, you get automatically, for free, that the composition, the way we defined it, is unital on the left, because we chose to contract the equality on the left, right? And you also get for free that map sends identities to identities, because we just decided to contract the equality. What if we want to prove unitality on the right, or associativity? That's a bit more complicated, right? And the idea is that we have a dependent version of J that is precisely for this new judgment that I've just told you for equality of entailments. So this is what it looks like. And the intuition is pretty simple. If you have two dinaturals, alpha and beta, here, they are equal everywhere if they agree on Reffel, just on Reffel. And the signature here of alpha and beta is precisely the one that I've shown you for the J rule. Okay? And the hypothesis just says alpha and beta are equal on Reffel. And in the semantics, this is precisely dinaturality. You need dinaturality in this point. And actually, it's an if and only if. So this condition characterizes dinaturality precisely. And so from this, you can just prove unitality on the right. You have Reffel here. And then you have some f here. And you want to say that this computes down to the same f. Well, then it's enough to consider the case where f is Reffel. And you take this a and z, and they become the same w. And then this judgment above, this sequent, is just the computation rule on the other side, right? So on the left. And then you prove associativity for free, also. F, G, H. You take the case where f is Reffel here, and then everything computes down to this. And finally, functoriality, map f composed with G. You consider the case where f here and here is Reffel, and then you're done. And actually, the most interesting part of this tape theory is that you get something that people have been trying to do for a long time, is that you get naturality statements for free, again, from just directed equality contraction. You have if you have a natural transformation on terms from f to g, well, you just write down the statement for naturality down here, and then you take the case where f is Reffel, and then everything computes down by the rules that I've shown you before. So you're done. That's the whole proof. And similarly, you can prove that the functions that you're dealing with are natural, and you can also prove that they are dinatural. It's just a bit more involved. And the idea is that you use transport and then alpha. So actually here it's alpha and then transport. Or you can use transport and then alpha on different indexes, which I'm not showing here. And again, this follows just by considering the case where f is Reffel, and you're done. So you see, these are precisely the same steps you would think of by doing some elementary treatment of directed type theory. Now, we have the logical rules for the connectives of the logic. You have conjunction, for example. And the key idea, the key technical aspect, is the fact that these rules are stated as bijections. And we call this adjoint form because it's similar to the formulation in adjoints, or quantifiers and connectives as adjoints. So these are the rules for conjunction. These are very similar to the ones you might have seen in simply typed lambda calculus. And then the rule for implication is also very intuitive. It's just currying and uncurrying, with a small catch, the fact that when you take this a here and move it on the left side, whenever a variable was used correctly, well, now it's used incorrectly and vice versa. It's intuition. And then you have the rules for coends as adjoints. Again, these are not really adjoints because dinaturals don't really compose, but this is what they look like. So here, this is for all, and this is exists, and this is just exactly the bijection you see in the treatment of, for example, Loregian quantifiers. And using these rules, we can prove theorems in category theory logically. So this is just a list of the things we can prove in our system, using a logical interpretation and giving a logical interpretation to all of these. And actually, there's a very curious instance in which the type theory informs the category theory. So a very cute theorem you can show is that the limit over x of the colimit over y of hom is actually always a singleton. So it's pretty interesting. And this has a homotopical interpretation, right? But here we are kind of going backwards and informing the category theory. So this is what the proofs look like. This is the Yoneda lemma. You've seen it before. This is the coYoneda lemma. I'm just going to be quick through these. Then this is a proof that presheaves are Cartesian closed. This is a whole proof. And then if you've heard of CAN extensions, well, they also have a logical interpretation. They are computed with this logical formula here. For all, equality, f, and then implication. So if you didn't understand CAN extension, you can just look at this formula, and this is precisely the characterization that people use in category theory. And again, it follows similar steps as the proofs that you've seen before, as bijections. And then you can exchange quantifiers. This is called the Fubini rule. And that's mostly it. So just to conclude, we hope that this work gives us a deeper reason why dinaturals do not compose, because we don't really know the deep reason why. And my hunch is that this non-compositionality is intrinsic to CAT because in groupoids they all compose, and in postets it's also fine. And I would like to find some directed homotopical reason why they don't compose, like failure of UIP. And in the long term, we hope to use this type theory and the ideas behind it to do synthetic rewriting, synthetic models of type theory, because now my types are categories, and to revisit. There are more things that allow us to interpret category theory logically, which I haven't shown you here, but that's for future work. And in the immediate future, we're working on the dependent case. So we have a notion of dinatural context extension, so you can be looking forward to that. And that's the end. Thank you.
Questions?
Hi, thanks for the talks, very nice. I was curious, so when you kind of do this duplication of variable, they're kind of unrelated, but also kind of related a little bit. Is the reflexivity the only rule that really talks about how to relate x to x bar, or are there other things in the syntax where you need to kind of relate the two things in a way?
In some sense, REFL is the least one that relates them, but they also have to be related in the statement of transitivity, right? Because B appears.
No, but I mean, in a syntactic rule, this is the only one that does that, and then you can derive all sorts of other relations through that, or?
Not really.
Okay.
Not really. Yeah.
Thanks.
More questions?
So I have two questions, actually. The first is, do you have an implementation?
No, I tried. It's difficult because of the op. That's the very short answer.
And my second question is, OK, many people are trying to work on directed type theory, and you made an interesting choice to focus on the first order case and to bring up naturality. So dinaturality explains very well your design. But does it also explain things about the other designs? If you take existing in-progress work on Martin-Löf type theory directed, you restrict to the first order case. Do you see the same sort of behavior, something different? Can you explain the choice of your colleagues through dinaturality?
So my answer in general to this question is yes, it should inform the dependent case. The key observation is the fact that most directed type theories that you see in the wild are not really about the algebraic model of just one categories. They use geometric models, and in that context, things are very different. Even though they might look on the surface the same, actually the models are very different. So,
can I just ask the next speaker to set up, and you can...
Have you looked at second order?
Not really, but it's not too difficult, actually. It's not too difficult to insert a universe. It's fair, we can talk about that.
All right, let's thank Andrea again.